F statistic is found from the ratio of variance of the treatments over the error and is derived from an F distribution compared against an F critical value. There are several assumptions for this test, including each of the groups is a random sample from the population of interest, the measured variable is continuous, the error variances are equal, and the variable is approximately normally distributed. Tillman Chemical, as an example, is testing a new drug that they have developed, Plaque breaker X. The researchers will use ANOVA to determine the effects of variation among the 3 treatments for 3 populations, with 10 observations each. These include a control fibrinolytic, a competitor's new drug, and the Plaque breaker X. The observations will be averaged for each category. Then, an average for all the observations will be taken. These values will be used to calculate the sum of squares for the treatment, error, and total. These values will be used to determine the sum of squares, and via the ANOVA table, the eventual F statistic. For now, the researcher will just use them to calculate the sum of squares for the ANOVA table. Assuming that he has already done so, he begins to fill out his table. First, with the degrees of freedom for each value in the table, the total calculated by the total number of observations minus 1, the treatment calculated by the number of observations for one of the treatments, and error from subtracting the treatment degrees of freedom from the total degrees of freedom. We'll use this to divide each corresponding sum of the square value. Lastly, we divide the resulting treatment MS from the error MS to get our F statistic. We use an F distribution table with the error degrees of freedom and the alpha value of 0.05 that the researcher has so chosen for this experiment. However, the supervisor has requested by the division head to show his calculations for his sum of squares, and here it is. Lastly, does his F stat exceed his F crit? Let's look again at our F distribution. As we see here in the shaded region, this is outside of the null, or the rejection zone. This line in between both regions is our F crit, and the dotted line is our F statistic. As we can see, it is clearly in the rejection zone, and so we must reject the null hypothesis. There is no variation among the treatments. However, the researcher is still left with a problem. We only know that at least 2 of these groups vary significantly, but which ones? In order to determine this, we will use a 2-key test. First, we determine our critical value by finding the Q value for our error degrees of freedom and the alpha value, multiplied times the square root of our MS error over the total number of observations. Here we see our critical value calculated by our researcher. We find our 2-key statistical values by subtracting each treatment mean from one another and taking the absolute value. And here, once again, we see that our statistical values all exceed our critical values for the test. Thus, we may finally conclude that all of our variables vary significantly,